Go.
So, this is actually a story about an accident which led into something that kept me occupied for close to 20 years. So, without further ado. A long time ago, and it's probably longer than 15 years, I was working at Lockheed, and I was up in Palo Alto on Hanover Street. And I made a mistake. I did something kind of experimental, and I got myself into trouble. But it's a good kind of trouble. So this goes back to 1993, so it's probably over 50 years. There's a satellite that some people have heard of called Landsat. It was launched in the early 1970s. It was for land resource utilization. And it was very successful. It was 7-band satellite, so it had like infrared, red, green, and other kinds of spectral bands. Government loved it. They wanted to have a souped-up Landsat satellite. So there was a group called the Defense Landsat Program Office that was formed, and we did all kinds of studies. The problem is, when you have a large number of bands to send down, it's a huge amount of data. So we were looking at onboard compression, compressing the data on the satellite prior to sending it down. It's lossy compression, so we were looking at, well, what's the impact of the loss going to be on the algorithms that are going to be run on the ground once the imagery gets there? And that's what we did. So we were working on that. A couple of folks and I published some articles on how to measure the impact. And if you go back to Google and you do a search on our authors, the stuff that we did was seminal. And it was kind of surprising to me because it didn't seem all that advanced at the time, but it was cutting edge. So I was assigned to look at texture. There are all kinds of things you can look at with images: color, edges. And what I was looking at was being able to segment it into texture regions. Now, the classic article on texture is done by Bob Herlick and some of his colleagues way back about the same time that Landsat was out. Not a coincidence, because that's how they segment these kinds of images into farmland, deciduous, coniferous, etc. The thing is, in order to be able to do this kind of analysis, you need to be able to get down to the pixel level, individual dots in the image. And it gets pretty hairy. There's some pretty involved mathematics, a lot of arrays, a lot of summation across rows and columns. It's defined in neighborhoods, and so you have to do all kinds of summations and multiplications and ratios and things. It's very hard to code this. I wrote it in C, ran like a bat out of hell. It was really fast. Hard to code, but then how do you test it once you've got it coded to see whether it really works? So, it turns out about the same time, oops, go back. A very famous memo, if anyone here is a software person and they really like to have some fun, you can actually get a copy of HackMem. Buried deep in this little collection of fun things is an item. They have a whole collection of items. And they said something about munching squares or views of some graph. And it turns out that that particular picture has some really nice properties, and it makes it perfect for using as a test image for the texture analysis. Very easy to write. This is MATLAB. That's what it produces. It's fractal, it's self-similar. But if you start doing things like, what are the histogram of all the grayscale values? It's uniform noise, indistinguishable from noise. If you look at the co-occurrences of how often does a grayscale value occur next to one, all along the main diagonal, and if you zoom in really close, it's got some beautiful patterns, as one would expect from a fractal. So this is a perfect image. You get some known values, you run the code, do the values correspond to what you expect? Success. And so I generated this way back on a PowerBook. This is how long ago this was. And I wanted to bring the image up and look at the histogram, and I hit the wrong button. Instead of hitting the histogram button, I hit random pseudocolor. And that's what I got. So, and I'm not kidding when I say, so I worked for a very lovely lady named Sylvia Shen. Unfortunately, she's no longer with us. She graduated from Purdue. She was in image processing and statistics. So by the time she got to her office, and the printer was right outside her office, the toner cartridge was completely exhausted because I printed these out. And when I say there's a never-ending supply of them, there really is a never-ending supply of them. So, but that's all well and good. You know, art's fun, but I got to make a living. So science first and art comes later. And it turns out, can I reproduce what HackMem said? Yes. And if you use a certain grayscale mapping, you get an image that's exactly similar to the one that they talk about in the memo. And in fact, I guess back in '72 they didn't have a lot of color monitors to do what I was doing. And by varying, so it's 256 color slots, you know, to the 8th, and I pick a different value for red, green, and blue, there are a large number of triples that are possible. And of course, some of them will look like mud, but some of them look gorgeous. And so by varying how I map the bits of the row and the column, I can get different base patterns. And this leads, for the computer scientists and folks who are into electrical engineering, this gets into Boolean algebra. And it's 16 different ways that you can combine bits. Ands, ors, exclusive ors, equivalents, you name it. And it leads into a very, very nice rabbit hole. And this is what I'm talking about. So here are the 16 different ways of combining things. Imagine you've got a row and a column index. You take a little from column A, a little from column B, and use that as the grayscale value for the pixel that you're going to produce. You can go a little bit more complicated. I'm talking about individual bits. You can take groups of bits and do something very similar to fuzzy logic. In fact, it is based on fuzzy logic, which is kind of appropriate because Lotfi Zadeh is right, his office is right down the hall. I do all this iteratively. I take they're nested for loops. You saw what they were. But it looks recursive. So it's interesting in the sense that you can use iteration, which is very quick, to produce something which has recursive properties. In fact, the interesting thing about these particular images is they don't compress very easily because they're noise. There's no redundancy. So you try to compress this and reduce space, can't do it. This is one of my designs, and this is one of Mohawk's designs. They really are tiles. They can tile in every direction. So this leads to, I mean, you start asking questions, going, this is really fun, but it's with squares and rectangles. So what about other shapes, like triangles? And other, even weirder shapes, pentagons, hexagons. And then there are polygons, which aren't even polygons in the conventional sense, they're stars. You connect, instead of connecting this to here, you connect this to here. And it produces a polygon, but it's a weird looking polygon. Do they fit together? How do you seam them together? If you wanted to make quilts, how would you do it? And how many ways can you do it? And you can see, very quickly, it gets out of control. So I need some sort of a method, discipline, to be able to come up to deal with this. Well, let's say triangles. So you have a triangle, you pick a point inside. This is the only math you're probably going to see, except for those equations before. You can compute what the triangle area is very simply using a determinant. It turns out the area of the full triangle is equal to the sum of all the subtriangles. So you can imagine each one of these adds up to the area. Divide through by the area. You can have each one of these be a number between 0 and 1. They all add to 1. And I'll get to the next slide and you'll see where that comes from. There are other ways that you can say, I'm going to pick a point and then draw the perpendiculars, or the midpoint of each side. It's a different way of doing areas. This, by the order of vertices, is kind of important because otherwise you get a minus sign or plus sign. It turns out if you look at this and you produce something, there's a triangle which is a fractal, and this, if you study Pascal's triangle, you'll see that if you take all of the odd numbers in Pascal's triangle and color them black, and all the ones that are even, color them white, you end up that. It's the most basic fractal that you can see, except for a few other things that are out there, like population things. It's really, really primitive, but this is what comes out of this basic idea. And this leads to even deeper things where if you say, okay, let's draw perpendicular, this gets to something called trilinear coordinates, which if you go back to the 1800s, you'll find textbooks where they're obsessed with this stuff. And this also leads into the area of finite element methods, because this is what is used to figure out, if you know values at the corners of a polygon, you have a point inside, you can use the weights to determine what the value is inside. So this is kind of the stuff I get out with Quadrille Islands, using extensions to the basic methods I'm using. This is very similar to Frank Stella's work. And so when I get something that I consider to be sort of boring and I go, hey, it's like Frank Stella's work, I must be onto something kind of interesting. Pentagons. So this is using some different kind of star polygons, and I combined the coordinates of points inside and outside to produce these designs and then color them. Hexagons. Some of these are huge. This one here is so large it wouldn't be able to fit on the slide, and it looks like a tile mosaic. I have one that looks like a snowflake, a lace snowflake. Octagons. I actually put a few of these on stamps. We'll get to that, some of that later. This is where it starts. They start off looking black and white and grayscale. And so then what I do is I just do a simple paint by numbers to get some very, very colorful results. So now we're starting to get, how do we put them together? There are different kinds of tessellations. Most people are familiar. They look at the ground, they look at the tiles in the bathroom floor. This is regular tessellations because you're using a single design repetitively over and over. Semi-regular deal with two different kinds of designs, and the way they meet at junctures and edges determines if they're semi-regular versus demi-regular. So there's some mathematical rules that decide whether you're dealing with semi or demi. And this leads to quilting. Imagine filling each one of these spaces with a design that's algorithmic. That's one of the things I want to do, and one of the things I started to do at Jurassic, is to develop a toolkit. That's basically a pattern factory on a laptop. And it's sort of appropriate at the end of the year to start talking about how this crosses disciplines and crosses cultures. These are taken from some very, very old textbooks on art of the Alhambra. And it turns out that in the Islamic faith, there's a prohibition against making images of animals, living things. So they do abstract. And it's a good thing that they did, because look at the beautiful things that they produced. Celtic art, for the folks who are Irish. Ian Bain has a beautiful book on Celtic knots, but imagine filling those with designs. Leads into topology. Now, underlying all of this stuff is mathematics, and the mathematics deals with crystallography. Because what I'm dealing with here is two-dimensional wallpaper groups, and there's 17 of those wallpaper groups. These are the notation for each of those groups, and they relate to whether they're mirrored symmetry, glide symmetry, and where the center of the reflection or duplication is. It's interesting historically to note that there are 230 groups in three-dimensional space. In two-dimensional space, there's 17. You'd think that they were easier to find. It turns out all 230 were categorized before all 17 were nailed down. And so this is a catalog for the two-dimensional space. For the three-dimensional space, you can send about $200 or $300 to the International Union of Crystallography, and they'll send you some really beautiful books that nail down this stuff very precisely. But the interesting thing is, this is all mathematical, but the world arrived at these conclusions empirically. If you look across all the disciplines, all the various places in the world, people played around with these ideas and came up with these groups independent of one another, which is really kind of, it's sort of satisfying that there is one thing that unifies everything together, and people gravitate towards that. So here's one of my tiles. I take 4 of these guys, I move down, this, there, colorize, and that's what I get. It's simple. Things get a little more complicated if I want to take this and make 1 in the center and then 7 total. This is only 25% resolution. And then again, this gets back to what I was saying earlier about the fact that across all disciplines, across religions, across nationalities, across regions, this is the one thing that unifies everyone, is the appreciation for this type of beauty. So what's next? And so I have, this is only a partial list of my to-do list. All sorts of extensions to be able to allow assembly of very complicated things. Different color systems than just RGB, being able to go into perceptual color space. Different ways of doing fuzzy logic. All of these different kinds of tessellations. There's stuff that Coxeter has done, stretching, warping, you name it. And you can see that it touches all areas in engineering and science. And we're all familiar with planar geometry, where everything is nice and flat. There is elliptic geometry, where you're dealing with things on a sphere or an ellipsoid. And there is hyperbolic geometry, where you're dealing with saddle surfaces. These are also tessellated. So imagine a hyperbolic plane where you've got a saddle surface. You're looking down, and you can see as you move away, there's distortion as a result of the curvature. Here, you're looking at the surface of the sphere from inside the sphere, and you're seeing a hexagonal tessellation. And then I'm starting to colorize them to see what I can get out of this. So, if you look really closely, and almost, you can see at the corner here, there's a compass. And I use that motif very, very specifically, because a lot of what's going on here is research. It doesn't look like it, but it is. Areas in finite element methods, a lot of the stuff that's being done here is cutting edge compared to the stuff that's currently being done with triangles and quadrille islands. So this is exploring ideas and areas of investigation in a different way. It's more sort of an appreciation, aesthetic way of doing things. So I wanted to conclude with some quotes by some folks I really appreciate and respect. In fact, I had a few that I had to leave off from Feynman and others. But specifically Blaise Pascal's one, which talks about that you're moving around in a very, very large domicile, and there are areas that have not yet really fully been explored. So this is kind of really an appreciating kind of thing. So when I was at Jurassic, I was with a bunch of other artists for 1 month. And the folks saw this, and the first question they asked me is, why is this your first residency, and why aren't you rich? And I said, well, I never really had that much time to explore that. And someone said, you really should put this on fabric. And I said, okay, I'll give it a shot. And so these are small scarves. In fact, this design is based on the artist's barn at Jurassic, where it's a 12-sided barn, and in the center there's a raised area which is where the library is. So I pieced together a design with that. And I think you may have seen one of these in the slides. This is, I believe, a 10-sided object where I colorized it. And then I have another version of the Jurassic where I colorized it slightly different. Same basic pattern, only thing is a different color map. And what you see is, by picking the color map differently, you can emphasize and de-emphasize different aspects of the design. And my wife, we're going to celebrate our silk anniversary at the end of this month. And here are some larger ones. I'll pick one. And we also sent out some cards, which have, this is the lace snowflake I can pass. You can look at that. And then one of the other designs. This was from my artist page. Everyone at Jurassic, when they leave, have to produce a single artist page. It's enormous. So, this is 42 inches by 42 inches. One of
The color
Turn it around so we can see the other
Absolutely.
side.
Absolutely. You can take all of these, actually. So,
How are you printing those?
there's a company in South San Francisco called DPI, and they directly translate whatever image you've got onto silk. And in fact, I was too embarrassed to wear it, but I have a shirt where I took one of those designs and it's completely made out of a pixel.
How many pixels on the side for one of the large images?
It really comes, for those, I may have made a few mistakes in the sense I didn't pick images that were large enough. I could do 4K by 4K or 8K by 8K. But that's 42 inches square. And I think that's about the largest square one I could do. I have ones that are even more enormous. I have ones that are several 100,000 by several 10,000. I have one printed I took it to FedEx, Kinko's, and had it printed. It was 1 yard by 1 yard and framed it.
Have you thought of